Hello friends, this is Dr. Sangeeta Joshi from Vidyalankar Institute of Technology. Currently we are studying the course which is a lab course that is Fundamentals of Logic Circuits. In the last video I have shown you or demonstrated you the operation of the multiplexer in LT Spice, and today we'll try to understand how full adder can be implemented using 8 by 1 multiplexer in LT Spice. To start with, let us recap the fundamentals of full adder. So this is the symbol for the full adder, wherein we know that there are three inputs. Here I have designated those inputs as A, B and carry in, which is normally from the previous column. And there are two outputs, sum and carry. So these are the outputs and these are the inputs. If you look at the truth table, there are three inputs, so there are 8 combinations right from 000 to 111, and we already know that the sum and carry. So if you work out, you will find that at the position 1, 2, 3, 4 and 7, output is 1 for the sum, and at the positions 3, that means whenever the ABC in is having a combination of 0, 1, 1, 3, 5 and 6 and 7, the output is 1, 1, 1. And in terms of the min terms, whenever you are writing the min terms means wherever your truth table is giving you the output as a 1, that a combination is treated as a min term. So here for the sum, the min terms are 1, 2, 4 and 7. So 1, 2, 4 and 7, and for carry the min terms are 3, 5, 6 and 7. It is shown here 3, 5, 6 and 7. So today we'll try to implement this full adder using the 1 of 8 or 8 as to 1 multiplexer. That means there are 8 inputs and single output. Now which IC we are using? Either 74151 or 74251. So before we start, let us look at the layout or the pin diagram for the IC. So this is 1 of 8 multiplexer, and you will find that there should be 8 inputs. So here is the D0, D1, D2, D3 and D4, D5, D6, D7. So these 4 inputs from this side, 4 inputs from this side. So these are the 8 inputs. Now how many select lines it will require? 3 select lines, because 8 inputs are there. So A, B, C, these are the 3 select lines. There are two outputs. One is the Q and another is the Q bar. So it is in a complementary form also output is made available. VCC and ground are the two pins, and strobe, that is the enable pin for the circuit or the IC. And here is the again the truth table for this IC, you can say multiplexer. So these are the 8 combinations, and for ABC, any whenever strobe is 1, whatever may be the value of this, you will always get a Q as a 0 and Q bar as a 1. So in order to make the multiplexer enabled or activated, you will have to have the strobe signal as a 0. You can see here strobe is always 0. So strobe has to be grounded, or the enable pin. Sometimes you will also find in the datasheet enable pin. So that is to be grounded, and then only we can route the data from one of the inputs to the outputs based on these select lines. Okay, these are only the select lines shown, and whatever is the data is available on the data inputs, that is made available to the output. Again, here you can see, so output is D0. Whatever is on the D0 is made available here. Whenever it is 1, it is D1. Whenever it is 2, it is D2 data would be available. And here the complementary data is available. So I have shown the schematic of full adder implementation using MUX in LT Spice. So this is the 74151 IC I have used. So it is a 8 by 1 MUX. There are two ICs we are using because we are supposed to have the minterms for the or the output for the sum as well as for the carry. So two separate ICs we are using. The same S0, S1, S2 signal we are giving from the three voltage sources. So here it is the frequency or maybe time period for one cycle is 2 millisecond, then for S2 it is uh, S1 it is 4 millisecond, and for S2 it is 8 milliseconds. So this is also we have considered the same in the multiplexer operation. And now what one is supposed to do, whatever is our minterms are. So what we had seen in the earlier case, our minterms are 1, 2, 4, 7 for sum. So you can see here this one means I1, I2, I4, and I7. This is the last one. So these all four are connected to the DIN, and this voltage source is given to the DC 5 volts. That means here all it is connected to logic 1, and rest of the data inputs are connected to the ground. Similarly, for the carry, you will find that we had considered here, minterms are 3, 5, 6, and 7. So you will find that 3, this is I3, this is I5, this is I6, and I7. They are connected to the data input, and that is nothing but 5 volts. So we have constant 5 volt. There is nothing like the various different frequencies, because that operation already we have seen. Now there is a data. Maybe that data is connected always to the 5 volts. That means the logic 1. So whenever based on the operation, based on the signal on the S0, S1, S2, based on which combination of the inputs are. So based on that, basically this would be made available at the as a sum. That means actually here S0, S1, S2, what we are using here, S0, S1, and S2, these although are the select lines, we are using these three lines as a data inputs. That is our data inputs. So based on what is the output that we are getting as a sum. If you can see here, although I have written here A, B, C in, but now in multiplexer I have connected it to the S0, S1, and S2. So based on this, what sum and carry I am expecting. So that is what I am finding here. So actually this is nothing but my A, B, and C in. So based on that, one of the, no, this is permanently connected to 1. So basically I am expecting the output to be 1 whenever the minterm is satisfied. And similarly here for the carry also, appropriate signals are given to the ground, appropriate inputs, and as per the minterms, it is connected to the DIN. And I can also show you the waveform so that you will have a clear idea. Now see, S0, S1, S2. So S2 is the MSB. It is nothing but what? It is nothing but your A, B, and C in. It is as good as A, B, and C in. So I have written here, this is the first is the I am applying the 0, 0, 0. So 0, this is the 1. That is the 0, 0, and this S0 is 1. So this is the 1, this is 2, this is 3, this is 4. So that combination I am applying here, 5, 6, and 7. So there are two outputs, sum and carry. So let us understand first the sum. So what are the minterms for the sum? 1, 2, 4, 7. That means what? For all these 1, 2, 4, 7 combinations, I should get the sum as a 1. And that is how you can see here, 1, 2. So I am getting the sum as a high, sum as a high. So I have marked this in a red color box. Then 4, I am getting again the sum high. So you can see this is a sum signal. This is a S2 signal, this is S1, and this is S0. And finally the 7. So for the 7th, that means 1, 1, and 1. So this is actually decimal 7. So for that also I am getting the sum as a 1. So my truth table of the full adder is verified. Similarly, for the carry, it is 3, 5, 6, and 7. So you can see here for the third three number, that means whenever S0, S1, and S2 is having a 3 combination, you can see this is 0, this is 1, and this is 1. 0, 1, 1 is nothing but 3. So we are getting a carry. And here carry as a 1. And here I am getting a carry 5, 6, 7. So 5, 6, and 7. So for all these three combinations of the inputs, I am getting the carry from here. From here onwards, you can see carry is always high till the end. So that means my full adder truth table or sum and carry for various input combinations result is verified. Now let us look at the same results using the LT spice. So this is the diagram which I have already explained you, and I'll just run this. So we'll make it windows tiles vertically. So these are the same results I am getting. See, S0, S1, S2, sum and carry. So for 0, 1, 2, 3, 4, 5, 6, and 7. So for 1, for 2, for 3, 4, and for 7, I am getting sum as a high. You can see here sum is getting high. And this is only for the 0, 1, 2, 3, and then 4, 5, 6, 7. 5, 6, and 7. Carry is high. You can see here carry is high. So that is what I explained you in the through the PowerPoint presentation. So if you build a schematic in this fashion, and you will definitely get the full adder implementation using the 74151 IC. Thank you.